This section covers many more trigonometric identities, some of which you use often enough it's helpful to memorize them, and some of them, like sum to product and product to sum, we'd see a little later that you don't use as often, but you need to be familiar with them. First of all, the double angle formula for sine 2x, think of that as sine of x plus x, and then using our sine addition formula, sine of the first, cosine of the second, plus cosine of the first, sine of the second. So there's two of these, you just get 2 sine x cosine x. So here's our identity for double angle formula for sine. For cosine, do it the same way, cosine x plus x, use the cosine addition formula, and you get cosine squared minus sine squared. And that's one way to express it. Now, because we have the Pythagorean identity that cosine squared x plus sine squared x is equal to 1, you can use this and substitute it in here in different ways to get these other two forms of the double angle formula for cosine, which are sometimes very useful. Okay, looking at some examples, this is a multiple angle equation, so 2 cosine x plus sine 2x is 0. So what we can do is express sine 2x as 2 sine x cosine x and then factor. Once we factored, solutions would be either when cosine x is 0, which are these two, or when 1 plus sine x is 0, or sine x is negative 1, which is this one here. And if you want to generalize the solutions, you can do it this way, even though you really wouldn't need to have, some of this is redundant, but if you just want solutions from 0 to 2 pi, then pi over 2 and 3 pi over 2 would be fine because you've already got this one over here. Okay. Here we have the cosine of an angle. We know it's in the fourth quadrant. We want to find sine 2 theta, cosine 2 theta, and tan 2 theta. All right, so sine 2 theta is 2 sine cosine. Well, we know the cosine is 5/13, but we need to get the sine. So the way you can do that is to draw in a triangle. And so we would draw back up this way. We know that this is 5 and this is 13. And using Pythagorean theorem, we could get negative 12. So that's how we got the negative 12 down here. So we know the sine of the angle is negative 12/13, so we can negative 12/13 there. If we want to get cosine 2 theta, we can use the version that only has cosines in it. Looks like this, and plug in 5 over 13. If we want to get tan 2 theta, you could just divide these two. Sine 2 theta over cosine 2 theta, the negatives and the 169s cancel, and you get 120 divided by 119. Okay, this is a triple angle formula, which we don't do very much with, but it just illustrates a couple different concepts. If you want to do sine 3x, first express it as a sum, sine 2x plus x. Then use this sine addition formula. Then we use double angle formulas to make sine 2x into 2 sine cosine, and cosine 2x into 1 minus 2 sine squared. Now we could have picked any one we wanted as far as the 3 cosine 2x's, but we're trying to get it all in terms of sine when we're done, so we picked the one that's only got sines. Cosine times cosine becomes cosine squared. We distribute the sine x to get to these two. Cosine squared I write as 1 minus sine squared using the Pythagorean identity, and then I distribute stuff and simplify until I get all the way down to here. Okay, more formulas. These are power-reducing formulas. You start with the squared, and now you don't have anything squared, and same with these two. So you're reducing powers. So these things basically are derived from the double angle formula for cosine, but they can be very useful. And so sine squared and cosine squared, you see they're very similar for power reducing, except the sine squared goes to minus, cosine squared goes to a plus. Here's the tan squared. You can get by just dividing the two of them. So here's an example. We want to take sine to the fourth and write it as just first powers of cosines, just first powers. So first I read it as sine squared quantity squared. Then using a power reducing formula for sine squared, I get to here. The 2 on the bottom, I square it, and it's a 1/4 out front. Then I FOIL this part to get these 3 terms. I still have something squared, so I've got to use another power reducing formula to get to here. Notice that now 2x becomes a 4x because you double each time, u to 2u, x to 2x, 2x to 4x. You double it when you reduce the power. And so then it's just a matter of doing some algebraic steps to get common denominators. You get all the way down to here. Okay, here are some half angle formulas. So sine u over 2 is plus or minus the square root of 1 minus cosine u over 2. Cosine u over 2 is similar. Here's tan u over 2. These guys, again, are based on the power reducing formulas. The plus or minus doesn't mean you get 2 solutions. It just means you have to really pay attention to what quadrant you're in. So for instance, if you want to find the exact value of sine 105 using a half angle formula, we know that 105 is half of 210. We also know that that 105 is in quadrant 2 and sine is positive there. So when we're done, we want to have a positive answer. So that's why we don't put a plus or minus here. So sine 105 is square root of 1 minus cosine 210 over 2. Cosine 210 comes out to negative rad 3 over 2, so we get to here. And then using some algebra, we can get to this solution right here. Okay, here's a comparison. This is cosine of 165 degrees, and we want to get an exact value for it. Here's one way to do it. This is the way we've done it using a cosine addition formula. 165 is 120 plus 45. We use our cosine addition formula, cosine first, cosine second, change the sign, sine first, sine second, get out our unit circle, know all the values, and we get all of these, and simplify it to get to here. Using a half angle formula, 165 is half of 330, and so plus or minus square root of 1 plus cosine 330 over 2. Cosine 330 is rad 3 over 2. I do some algebra in here by getting a common denominator in my numerator. Bring your 2's down. Then this 2 squared comes out front. And finally, 165 is in quadrant 2, and therefore we expect cosine to be negative. So we have to keep the negative there. Okay, a few more formulas. And this would be the product to sum formula. So you see we have products and we can make them into sums. So we have those formulas, and these formulas in the next set are generally they're very easy to use as long as you know them, and you'll be given them generally. And it's just a matter of matching up the correct template. So if you see a cosine with a cosine, use this one. If you see sine cosine, use that one. Okay, and then we also have sum to product. So sine plus sine gives you this one. Sine minus sine gives you this one. So the point is that the angles are different. So these formulas allow you to make some simplifications. So let's go back and go through a few more sample problems. Here we have cosine of u is negative 2/3, and we know we're in quadrant 2, and we want to find values for sine 2u, cosine 2u, and tan 2u. And so sine u is rad 5 over 3, and the way we can get that is by drawing up a unit circle, and we say adjacent 2, hypotenuse is 3. I made this negative because it's in quadrant 2, you're going left. So Pythagorean theorem says this is rad 5. So now opposite of our hypotenuse, the sine is rad 5 over 3. So now that I've got these two values, very simple to expand these and plug in the values. 2 rad 5 over 3 because that's sine, negative 2/3 because that's cosine. We get to here. For cosine 2u, I use this version this time. So it's negative 2/3 squared minus rad 5 over 3 squared, negative 1/9. And finally, for tan 2u, I just did sine 2u over cosine 2u. And so I multiply by the reciprocal, and I get 4 rad 5. Over here, we want to simplify this. So we want to reduce the powers. So power reducing formula. Then 2 over 2, got a fourth here. The 2's become a fourth. These guys is the difference of two squares. So the 1/4's out here. Here's my 1. Use another power reducing formula in here. And then 1/4's out here. I get I fix this up, these two pieces up a little bit. And by getting the common denominator simplifying, and I get all the way down to there. And then for this one, this is a product, and we want to write it as a sum. So we use our product to sum formula for two cosines. And basically it's 1/2 cosine of the difference plus cosine of the sum. And so we get cosine negative 2 theta plus cosine 6 theta. Now cosine's an even function, so cosine negative 2 theta is the same as cosine of positive 2 theta, which is good because otherwise you might say, well, why did we do 2 theta minus 4 theta instead of 4 theta minus 2 theta? And it turns out it doesn't make any difference.